Good evening, everybody. Today is day 23 of Math 133, and we're going to look at the Chapter 10 project. It is on page 574 in your course pack, 574. Um, so before we do that, we need to talk about April 16th. So Thursday, April 16th. I'm not going to be available in the evening, so there's not going to be an evening class that day. I dropped a link in the chat with what you want to do. So we have two options, and uh, I need you to go in here and select which of these two options you like better for the morning class. Now, I know you're not taking the morning class, you guys are the evening class, but so I still want you to answer this. It'll take you like a second. So option one is I run the Zoom in the morning. We're going to be looking at the Chapter 11 project that day, and I'll record the entire session. And then everyone on the evening call, you'll have to just watch the Zoom and still turn it in by April 21st. So that is option one. Okay. Option two is we don't have the evening class and we don't have the morning class either that day, and we push everything a day later. So if we did that, so uh, April 16th, the Chapter 11 project would get pushed to Tuesday, the 21st, and then the due date would get pushed as well. So we'd also push the Chapter 11 review. Those are the only two that we would move. And then we would cover the Chapter 11 review on Thursday, April 23rd. If we do that, um, right now we have 2 days set aside to talk about the sample final exam, and we would just cover it in one day. Okay. Now that's not outrageous. If we compare that to the midterm, we didn't have any days set aside for the sample midterm. We just kind of did a question here. We did another question here. Like we did a page of the sample midterm here and there. And then Cindy and Elaine also had some days that they had set aside for the sample midterm. And they also have 2 days set aside for the sample final exam. So we're actually still, even if we do push everything a little later, we are still ahead of the game. So we would still get more time to cover the sample final exam than we had for the sample midterm. So either one of those is fine, but let me know what your vote is. You don't need to vote for it in the chat. You can, I need you to vote in the link so that I can count up all the responses and we'll go from there. Okay.
Hey Joe,
So,
I have a question
yeah,
about that. So you know
sure.
how people who don't come to your classes and you do like the little hint stuff and stuff like that, like you only like are you gonna do that when you do the recording or are you gonna do it like
No, I would record the entire session.
okay,
Um, and I generally, so I do that usually when we're looking at the chapter review worksheets,
okay.
and I give you some hints for those. For the projects, I've been recording the entire session for the projects. Today, we're going to be looking at the chapter 10 project, and I plan on recording the entire thing. I recorded the entire thing this morning. Part of the reason why I'm going to record the entire thing is because even if you follow along with the recording, your answers are going to be different from mine, okay? Because you had different counts for your M&Ms and Skittles. So you might need a little more help since your numbers aren't going to match mine, right? It's about the methods and it's about understanding how you do the calculations, as opposed to on the chapter review, where if you just copy my exact numbers, you get the exact answer, right? So I would record the entire session. Um, Anyway, let me know what your thoughts are uh, for April 16th. Regardless of which option you guys pick, there won't be an evening Zoom. So it's up to you whether you want to watch the morning Zoom that day or we push everything a day later. So, speaking of the sample final exam. The sample final exam uh, is going to be due April 30th. And I'm going to be sending out some information about the final exam, so be on the lookout for that. But the final exam is very similar to the midterm. You when you took the midterm, you were able to take it two different ways. You could take it at the testing center, or you could take it with me on Zoom. And the same thing is going to be true for the final exam. So you can take the final exam at the testing center Tuesday, Wednesday, Thursday, or Friday, the week of final exam. So that would be Tuesday, April 28th, or April 29th, April 30th, or Friday, May 1st. Okay, Friday, May 1st would be the last chance to take the exam at the testing center. Okay. And at the testing center, you can still bring your exam notes packet. You can bring two 8.5 by 11 pieces of paper, both front and back. So yeah, so be on the lookout for information about the final exam. If you want to take it with me on Zoom, we will be doing it on April 30th, same times that we did the midterm, which was we started at 9 a.m. for the morning class, and we'll start at 6 p.m. for the evening class, and we'll go for 3 hours. Now, I will point out that the midterm was 9 pages. The final exam will be 12 pages. So it's a little longer. It's about 25% longer. So, it's not huge. If you were doing the midterm, a lot of people finished the midterm in like 2 hours. That would just mean that your time on the final would be like 2.5. Okay, so not a huge difference. Now, if you ran out of time on the midterm or you were getting close to running out of time, the final exam is slightly longer, and so you might consider taking that at the testing center. Okay. Um, so at the testing center, as long as they're open, you get the entire time. So uh, make sure you get that time set aside. We don't want anyone to show up to the exam late and not have enough time to do it all. Okay. So make sure you have that time set aside in your schedule. I'm telling you the time of the date of the final right now. Okay. And you knew it at the start too. So be ready. Make sure you've got everything arranged so you can take it. Um, anyway, so uh for the um let's see, for the sample final exam, uh yeah, that one is the sample final exam is the best way to study for the final. So we'll be looking at that. Um and I think that's all I have on that. Let's jump into our project for the day. And that is again on page 574, 574. Okay. Um, in addition to the page 574 in your course pack, you're going to need two more things. You're going to need your data on your candy. Okay. So you had M&M and Skittle counts, right? So we're going to need those. And I told you, make sure you have those saved in a spot where you can find it. So these are my numbers. Your numbers will be different from mine, right? But I don't want you to have to go buy new candy. So go and find what numbers you had. You're also going to need this Math 133 Random Levels of Significance StatCrunch link. So you can find that in Canvas, or I can drop it in the chat for you. In Canvas, if you click on the Chapter 10 project, there's a link for random levels of significance. When you click on that, it takes you here. And make sure you sign in, and I'll drop this in the chat, okay? All right. So there's that, and there you go. Okay. All right. So use the level of significance to generate two random levels of significance. To do that, we're going to do data, sample, and then choose levels of significance and sample size of two. And you're going to write the two numbers you get here. Totally spilled water on paper. Uh, so we need two random levels of significance. Level of significance is your alpha. Okay. Alpha, you'll remember, is your error, right? When we were doing confidence intervals, we shaded in the middle of the normal curve, and the outside edge, the outside tails, we left those white. Those were our alpha, and we wrote it as alpha over 2, right? Z alpha over 2. Um, so the confidence level is related to your alpha. You want high confidence. You want to be very confident, right? So a 95% confidence is something that's common to see, which would mean that your alpha would be 5%, okay? 5% alpha is a very common alpha to use. Now, sometimes you want to be more confident, you want less error, and so you might see an alpha that's like 1%. Um, Sometimes, though, it's not a good idea to make your alpha too small, okay? Because if you make your alpha too small, um, there's two types of errors, and alpha is how likely you are to make a type 1 error. But if you have a very small alpha, then you have a higher chance of making a type 2 error. So maybe that's a problem, and so you should consider doing an alpha at like 10%. Okay. So anyway, you want your alpha to be low though. You don't want an alpha of like 20%. That's ridiculous. That's way too high. Okay, but um, so in our level of significance file here, I've got one that's at 10.1%, 9%. Here's 5%, and then it goes all the way down to like 1%. Okay. Um, so anyway, um. So we're going to pick two of these numbers at random and then put them on our paper. Now, I'm going to point out that like when you are doing actual hypothesis testing, you don't just pick a random alpha. Okay, 5% is a common alpha, and if you're not sure what to pick, 5% might be fine. But really, when you are doing this analysis, these hypothesis testing, the first thing to do is to talk with whoever you're presenting this to, whoever your leader is, or whoever is asking you to do this testing, to make sure they understand like how important it is to pick the right alpha, okay? So you pick your alpha ahead of time, and you need to talk about, what happens if we make a type 1 error, what happens if we make a type 2 error, okay? Because sometimes a type 1 is worse, sometimes a type 2 is worse, okay? And if a type 2 is worse, you want to make sure alpha is might be a little bigger than you would normally think to choose, okay? So you can't just pick a random number. Now, for our case, we're not testing, how effective our vaccine is, and we're not testing like how safe our cars are, right? So we're not talking about people dying in accidents. We are, or from, diseases. We're talking about candy. We're talking about M&Ms. So if we make a type 1 error or type 2 error, who cares? Okay. So for this assignment, we're just going to pick two random alphas. Okay. But I want to point out that that is not what you do normally. Okay. You need to take careful consideration into how you pick your significance. Anyway, for now, we're going to do data and sample, and we're going to select our level of significance column. We're going to do a sample size of 2, and we'll hit compute. And we are going to write those two numbers on our levels of significance on our paper. 0, 2, 3. Oh my goodness, I can't write that now. Got my paper wet. That's a hot mess. Okay. Um, okay, so once again, what I did was I have that link in the chat. I went data, sample, selected levels of significance, sample size of 2, and hit compute. And I got 2 different numbers. I wrote both of those numbers on my paper here. Okay. This one is what we're going to use for M&Ms. This one's what we're going to use for Skittles. Okay. All right. All right. Testing a claim with M&Ms. So, which M&M color had the highest count in your sample? If there's a tie, just choose one. Uh, Fill out this table for that color. Um, Note that if p hat is close to 1/6 or 1/6 as a decimal is 0.166666167, choose the color with the second highest count. The reason we want to do that is when you're doing hypothesis testing, um, eh, you're trying to tell if the sample that you have, the p hat, is really far away from a certain number or not. We're going to be comparing it to 1/6. Okay. And so if it's very close, like if your p hat is 0.168, then you're going to have a hard time differentiating that there's something weird going on in your sample. Now, honestly, you can kind of ignore this. I'm not sure why they put that in there. So, um, for now, let's just get what our highest one was. Okay. So my highest for M&Ms was orange, and I had 28 orange out of a total of 140 M&Ms. Okay. Um, so p hat, you'll remember, was x over n. So I need to do 28 over 140 in my calculator. 28 divided by 140 is 0.2 exactly. That doesn't happen. Um, so uh so if you get something crazy like 0.2379, blah 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 blah, just round that to the nearest 3 decimal places. I'll put 3 decimal places for here as well. Um so mine is 0.200. Yeah, so Gabby's is 0.267. That sounds fine. Okay. And yeah, I'm not really going to compare it to p hat 0.167, choose the second highest. I'm going to ignore that. Okay. You don't need to worry about that. Um, so Willy Wonka is bothering you again. Yeah, why is it Willy Wonka bothering you? Like, he wasn't uh the bad chocolate guys, right? So like in the book, wasn't it like Prodnose and Pickle Gruber? They were like the bad chocolatiers. I don't know. Anyway, Willy Wonka is bothering you, and he claims that more than 1/6 of M&Ms are my color, which is orange. More than 1/6 of M&Ms are orange. Write the appropriate hypotheses to test Willy's claim. Use a fraction, not a decimal. Okay. So we're gonna write our null hypothesis. And the null hypothesis is P equals, it's always equals, okay? And in this case, we want to test it against 1/6. Okay. We could write that as 0.1667, but they told us to write a fraction, so we're going to write it as a fraction. Okay. So your null hypothesis is always P equals. Now we don't actually know what P is, and we can never know it because we would have to test every single M&M in the world. We'd have to count all of them and see if 1/6 of them are orange or not. Okay. But we have done a sample here and gotten p hat, which we assume is close to the true p-value. And what we're trying to see is if there's something weird going on where they're making more oranges than they should be. Okay. Now, it already looks like, hey, I have more orange than any other color. So why can't I just say, yes, there are more oranges in the world than any other color? Well, because this was just one sample. Maybe my first bag had more oranges than any other color. Maybe even my second bag has more oranges than any other color. But that's not, you can't just go off of those and say, oh, well, then every bag is going to have more oranges, right? Now, on the other hand, if like all of my bag was oranges except like three or four candies, three or four of the M&Ms were not orange, then you can say there's something weird going on, right? And that's what hypothesis testing is doing, is it's looking at your sample that you have and it's comparing it to this and saying, is it so far away that there's no way that a random sample could have caused this? There is something weird going on. Now, if the true p-value is not 1/6, but it's like, I don't know, if there's one single orange more than all the other colors in the world, right? There's a trillion red, there's a trillion green, there's a trillion blue, there's a trillion and one orange. Well, okay, so sure. Then in that case, there is one more orange in the world. So the P is not 1/6. But there's no way you're going to be able to tell that with a random sample, right? What hypothesis testing is going to do is it's going to say if there's something that's so crazy that there's no way that this could have happened with a random sample. Okay. So it's still not perfect, because it's a random sample, right? Just like when we were looking at confidence intervals, we could never be 100% confident. We could be 99% confident or 95% confident, but there was still a chance we would make an error. And there's still a chance you'll make a type 1 error or a type 2 error here, okay? But those chances are very low, okay? All right. Anyway, so the null hypothesis in this case is p equals 1/6. The alternative hypothesis, which you can write it as H1 or you can write it as HA, either is fine. If you write H1, it makes it feel like there's supposed to be an H2, but there's not. Okay. Um, you can only ever test against a single hypothesis. Okay. And it's going to be p either greater or less or not equal to 1/6. In this case, he's saying more than 1/6, so he believes that it's this. Okay. All right. So there's that. Now I mentioned earlier that uh, when you are doing actual hypothesis testing, you want to, start by picking your alpha and be careful about how you pick your alpha. Another thing to point out is we actually did these in the wrong order. Um, when you're doing real hypothesis testing, you don't go get your sample and count the things in the sample. You don't go and inject a bunch of people with your vaccine and then start talking about hypotheses. Okay. This is actually the first step. Then, after you've set up your alpha, set up your hypotheses, then you would go and collect your sample and test it and see what happens. Okay. It's a minor detail, but technically, while we are doing our hypotheses, we don't actually know any of this. Okay. And that matters for the next question. Question number 4: verify whether all requirements to conduct an appropriate test of the hypotheses have been met. So we need to check and make sure that we've met our central limit theorem requirements, right? So we need to make sure our sample is random, it is independent, and it is normal. Yes? Okay. So for random, we would say yes. Every M&M had equal chance of ending up in our bag, right? So yes, every candy. had equal chance of being in my sample, right? Nobody went and picked out all the oranges, okay? Every candy had equal chance of being in my sample. Okay, independent, we need to check 20N is less than capital N. So my sample size was 140. Yours was different. Okay, that's fine. 20 times whatever your sample size was. That needs to be less than all M&Ms. So uh, is 2,800 less than the number of M&Ms? Yes, so it's way less, right? Absolutely. Yes, of course. Okay. Normal, we need to check NPQ has to be bigger than 10. Now, we don't know P, okay, and we can never know P. So I'm not, I shouldn't write NPQ. I should write what P value we're using here. Um, and with confidence intervals, we wrote P hat, okay? But I mentioned a second ago that we don't actually know p hat until we do the sample. So when you're checking your you're checking your requirements for the central limit theorem, this should be done before you take the sample to make sure you're getting a big enough sample. Okay, so um, I should be using P0 and Q0. Okay. P0 and Q0, those are my p-value from my null hypothesis. In this case, it's 1/6. Okay. It's a minor detail, and you'll see it on page 262. Page 262 is hypothesis testing for single proportions, and we have N, P0, Q0. Okay. Hypothesis testing for means is on page 263. Okay. We're looking at proportions because we're looking at what percent are orange. Okay. So in my case, N was 140. P0 is 1/6. What would that make Q0? What's Q0 in this case? Hmm. Good. Mike's got it. 5/6. So I need to see what that gives me. 140 times 1/6 times 5/6. Oh, nope, that's not it. You need to make sure that so when you're typing, you need to hit the right arrow so you can do the 5/6. All right, there we go. Gonna get 19.4. And that is bigger than 10. So mine is a yes. Okay.
Hey Joe,
Yeah, go ahead, Kevin.
can you say how you did the fraction again on Desmos? Cause that
Sure, absolutely. Um, so I did 140 times 1 divided by 6. So I didn't actually type a fraction. I typed 1 divided by 6.
oh okay.
And then I hit the right arrow and do times 5 divided by 6. Okay, so when you do divide, it is a fraction. Okay. I am curious, how much do you need for it to be um, bigger than 10? Oh, what am I doing? Times 5/6. So 0.1338. So if I do 10 divided by 0.138, shoot, that's not what I wanted either. 0.172. So if you have 72 candies in your bag, you got a no. If you did 73 candies, you got a yes. Um, so did anybody get a no for normal? Raya was close. She got 10.5. How big was your sample size, Raya? Was it like 75 candies? 76? Okay. Jordan got a no. She got 7.9.2. Sorry, 9.722. How big was your sample size, Jordan or Quinn? 70. So you were just under the 73. Okay. And Quinn was at 60, yeah. So, yeah, and like we saw in the chapter 9 uh project, uh oh, one decimal. Yeah, it doesn't matter. It doesn't say how many decimal places we need. So we just need to compare it if it's bigger than 10 or not. So just like in the chapter 9 uh confidence interval project, some people had no because their sample size might have been too small. That's okay. You aren't going to get marked down or anything for that. I don't need you to go buy more candy or anything. But I wanted to point out, like, when you're doing this hypothesis testing, it's important that your sample size is big enough. If we were doing like an actual hypothesis test where we were checking to see like if our vaccine was successful or if our cars are safe or if our commercial is going to be effective, then it does matter that our sample size is big enough. Okay, because if it's not big enough, then our results are not going to be reliable. Okay. So anyway, if you got a no here, it's not a big deal. Because for question 5, regardless of whether or not your requirements are met, so even if you got a no, let's test our hypotheses from number 3 using the level of significance from number 1. Okay? Show all work, steps, formulas, everything. Okay? So there's 6 steps, and these are all on page 262. Page 262. Okay? So we already listed our hypotheses, but I am going to list them again. P equals 1/6, and our alternative hypothesis is P is bigger than 1/6. Okay. Um, so Quinn was asking a question about the um, requirements for normal. And he was asking, why does NPQ have to be bigger than 10? And it doesn't have to do with it being 50% of 20. This 10 comes from the central limit theorem, and we didn't really get into the math, and we're not going to get into the math on why it's 10 from the central limit theorem. Just like with the with means, n has to be bigger than 30. And we did the chapter 8 project where when we had n was 30, it started to look normal. Okay. But there is math behind this theorem that, like I said, it's a little more outside of the class than we're going to cover. So if you do end up going farther in statistics, we might revisit the central limit theorem and go a lot more deeper into why that is. Okay. So Quinn, I kind of don't have an answer for you. It's kind of just, well, that's what it is. So yeah. Um, Okay, moving on. So I'm gonna write out my steps. So there's my hypotheses. I'm gonna write out my alpha, which my alpha from number 1 was 0.029. Yours will be different, okay? So just write whatever random number you got from that StatCrunch, okay? And then step 3, we're gonna write out our equation to calculate z. Okay, and I'm going to call it z0 because that's going to help us remember we're comparing this to the null hypothesis. We're trying to decide if we're going to reject or not reject the null hypothesis. In uh, confidence intervals, we wrote it as z alpha over 2 because the alpha was the error and we split that in half. Okay. Um, anyway, it's just a z value. Okay. The formula for this is on page 262, and it's this crazy one right here. Okay, so it's p hat minus p0 over big square root p0 q0 over n. Okay, and we'll substitute in what our numbers are. So my p hat was 0.200. That was my p hat. Key zero is 1/6. I'm not going to write it as 1/6 because I've already got fractions inside of fractions. I don't want to make it even more fractiony. I'm going to write it as 0.167 if you're okay with that. Okay. 0.167 is my P0. My Q0 then in that case would be 5/6, which is 0.833 all over my N, which was 140. Okay. Now, there's two ways you can go about solving this. One way is you can use the calculator and put this in a Desmos, get your z-value, and then use the normal calculator, stat calculator is normal, and get your p-value. Okay. The other option is you can do stat proportion stats one sample with summary. I'm going to show you both. Okay. So first I'm going to do calculators. Now everyone should have the same p0 and q0. Okay. Your p hat and your n will be different. So you'll get a different z than me, but yes, Jadlin, yeah, all your P0, we're all comparing it to 1/6 because there's six candies, six colors in the M&M bag, so that's why we're using 1/6. That's what
Wait,
Willy Wonka was saying. He was like, "Hey, it's more than 1/6."
so I have a question. Okay. So the 20.200 is that you said that's our p hat, so I got
No, no,
0.276.
that's my P hat. Yeah, your P hat is yeah, different. So,
Okay.
yeah. And yeah, so the projects give you a chance to work with your own data as opposed to just copying me. And that's another reason why I try to record the entire thing, because even if you do follow along, your numbers are different from mine. So I do find that people might still struggle because you're writing down a different number than I am. Yeah. All right, so I'm going to calculate this in the calculator. I do need parentheses. If I type this in the calculator around the top, every fraction has invisible parentheses around the top, but you know they're there. The calculator does not. Oh, I'm in the wrong spot. I'm in Desmos. So I'm going to do 0.200 minus 0.167, close my parentheses, divide by SQRT 0.167 times 833 divided by 140. So my Z is 1.046 million. Like I said, your Z will be different from mine. That's fine. Okay. Now, every Z value has a corresponding p-value on the normal curve, right? And sometimes we have a probability and we want to get z. Sometimes we have z and we want to get the p-value, okay? So that's what I want to do in this case. So here's my z0, and I want to shade greater than, right? The alternative hypothesis is greater than. And whatever this shaded area here is, that's going to give me my p-value. I need to find that using StatCrunch calculator. So right now I'm doing it using calculators. I'll show you how to do it with StatCrunch in a second. So um, to do it with calculators, I need stat calculators normal, and I want greater than, because that's what my hypothesis is looking at. I'm looking at greater than, and I want my z value. I don't know my probability. That's what I'm trying to get. I want my Z value to be 1.0469, and that's going to give me my P value, which in this case is 0.1476. Okay, so once again, what I did was I did stat, calculators, normal, just like we did in chapter 7, switched it to greater than, put my Z value in, and calculated my probability. Okay, we did that in chapter 7, and that was on pages uh, 257, right? That's how we're doing normal calculations. Okay. So I'm gonna finish doing the rest of the steps, and then we'll go back and I'll show you how to do this in StatCrunch instead. Okay. Uh, so step 5, we need to compare our p-value and our alpha. Which one is bigger? My p-value is 0.1476. My alpha is 0.029. And in this case, my p-value is bigger. Okay. If the p-value is less than alpha, we reject the null hypothesis. Mine is not. Mine is the other direction. So I do not reject the null hypothesis. Okay. Now, we never accept the null hypothesis. Okay. We write it as we reject or we do not reject. Okay. Why that is because the null hypothesis is that P equals 1/6. And I can never actually be sure of that, right? We said earlier that if there was 1,000,000,001 orange M&Ms and all the other ones were 1,000,000,000, then in that case, P is not 1/6, but there's no way that you're going to be able to tell that, okay? So you can never accept the null hypothesis. You can either reject it or not, okay? When you reject it, you are saying that this sample is so different from the null hypothesis. There's no way that it could be happening randomly that I'm getting all these oranges. Okay. There's something weird going on. Okay. If you get a bag that's all orange, I don't know if you can say that that's weird. That's not random. Something strange happened. I don't know if you should eat that bag. Anyway. Okay. So our last step is we're going to write out our conclusion. And you're going to write there is sufficient evidence or there is not sufficient evidence. If you do not reject the null, then there is not sufficient evidence. If you rejected the null, then there is. Okay. So did you write the word not here? Then you'll write the word not here. There is not sufficient evidence to support Willy Wonka's claim. What is his claim? Support the claim. What was he claiming? That more than 1/6 of all M&Ms are orange. Okay. All right. So I'm gonna go back to step 3. So on step 3, after you've done your substitution and plugged in all these numbers, I said there's 2 ways to go from here. And it's the same as when we were doing confidence intervals. We could do it with 2 calculators, one in decimals, one in and then do the stat calculators normal. The other option is you can do it in StatCrunch using stat, proportion stats, one sample with summary. So what does that look like? So if we do stat, proportion stats, one sample with summary, we put in our successes. So that's how many orange I had. I had 28 orange. out of a total of 140 M&Ms. For confidence intervals, we did this button. Don't click on that. We want to stick with hypothesis testing this time, and we're going to put in that our P is equal to, our null hypothesis was 0.167. And you need to indicate whether you're doing a two-tailed test where it's not equal or greater or less. I'm doing greater than. That's our alternative hypothesis. Okay. With confidence intervals, we clicked this button. Don't click this button for hypothesis testing because it's going to confuse you. Okay. So we don't need that. You can get the plot if you want. You don't need it, but fine, whatever. So put in your X, put in your N, put in your P0, put in which direction you want, and hit compute. And here is my hypothesis testing results. So my Z value is 1.0468, and that's the same Z value that I got, 1.0468. Okay, round it up to 9, right? So that's my Z value. So I didn't have to do that in Desmos. I could have done that in StatCrunch. And then I also got my P value, which was 0.1476. So that's here. And then I clicked the button to show the plot. You don't need the plot. You can look at it if you want to, but you're just shading. Am I shading on the right? Am I shading on the left? Or am I shading both sides? Okay. All right. So Jadlyn, does that you wanted to see that again? Does that cover your question? Or are you still stuck? Mhm. Okay, great. Um, okay, so I want to pause here and point out that um there's a lot going on with hypothesis testing, right? There's 6 steps, right? But it's not just that. We're testing proportions, and some of the variables can be confusing. So I want to point out uh some of the, be careful with what symbols you're writing. So first of all, there's P. P is the population proportion. It's what percent of all M&Ms in the world are orange. And we don't know P. We can never know P. Okay. So instead, we do a sample and we get P hat. And P hat is close to P, okay, but it's never equal. Okay, it's close enough, right? And that's what we are going to use when we are calculating our Z value. But we also have P0. So there's P just everywhere. Okay. P0 is the number we're testing against. Okay. And P0 is something you choose when you're setting up your hypotheses. Okay. Before you take your sample. Okay. So we chose 1/6. Um, but maybe you would compare it to something else, okay? P0 is going to be a number. I mean, technically P hat is a number as well, but it's going to be different depending on what sample you're looking at, right? P0, on the other hand, it's just the number you're testing against, okay? But there's lots of different p values, and I don't want you to be confused because there's others too, right? There's the p value that we get here from the z value. Every z has a probability that goes along with it, and that's this p value. That p value is not the same as any of these other ones. Okay. That p value is what you compare against your alpha, and alpha technically is also a probability. So there's percents flying everywhere. And I apologize, but if you follow these steps, you'll be fine. Okay. Um, so the p-value is related to your z, and you're going to compare that to alpha, and that's going to tell you whether you reject the null or not. Okay. Alpha is the probability of making a type 1 error. Okay. So that's question number 6 down here. What is the probability of making a type 1 error in your hypothesis testing? So whatever number you got for your alpha, that's the number you're going to write here. 0.029. That was my alpha for M&Ms. Okay. A type 1 error is, you want to avoid errors, right? We want to be as accurate as possible. Okay. So, um, yeah, so in my case, a 2% or 3% alpha for a type 1 error is not a huge deal. Um, but so I did not reject the null. I said, no, I'm not convinced. So Willy Wonka is trying to convince me that the M&M company is making way more oranges than they should be. Okay, and I'm not convinced. Okay. Did anyone reject the null hypothesis?
Um, I think I do reject because my p-value is 0.0014.
Oh, very
Again,
small. Yeah.
yeah, against my level of significance from the random two samples we picked the numbers is 0.047.
Okay. Yeah, so in that case, you would reject the null hypothesis. Jalen says she rejected the null hypothesis as well. Okay. Now, I mentioned that we don't know P. Um, but in this case, we're going to cheat a little bit and say, well, the M&M company does make the same number of every color, so P is 1/6. So if that's the case, then we shouldn't reject the null hypothesis. So anyone that did, that's that's just based on your sample, okay? And so alpha is the probability of making a type 1 error. So even if you do all this stuff and you have a random sample, there's still, for me, I have a 2.9% chance that I'm going to make an error where, oh, I rejected the null, but I shouldn't have. Okay. So Isaiah rejected his, and that sounds good. Now, part of it is that our sample sizes are pretty small. Even 140 is not a terribly large sample size. Okay. Um, if I was doing this like for real and like the results mattered, like we're talking about like saving people's lives or not, uh, I would want my sample size to be in the thousands. Okay, and that's going to be a lot more accurate. Okay, I'm gonna have a lot less chance of screwing that up. Okay, so if you rejected the null, great, you rejected the null, even if technically uh, we shouldn't have. Okay, that's fine. All right. That was for M&Ms. We're gonna do a lot of the exact same steps for Skittles on the next page. Uh, when we talk about which Skittles had the lowest count. So which Skittles had the lowest count in your sample? If there's a tie, just pick one. Fill out this table. I'm not gonna worry about any of this. Okay. 3 decimal places. Okay, so what did I have for Skittles? My lowest, actually, I had a tie. I had 42 orange and 42 purple. So just pick one of those. I already did orange for M&Ms. I think it's interesting that I had the most orange, but then the least orange for Skittles. I'm gonna do purple. I like the purple ones just a little bit more than the orange ones. Orange ones are still good. I like the orange ones, but purple's a little more delicious. I had 42 out of 238 purples. So my p hat, I need to divide those. 42 over 238. My p hat is 0.176. All right. All right. Willy Wonka's bothering you again. You need to block him from your phone. He's bothering you and claims that the proportion of Skittles that are your color from number 7, so mine was purple, is different from 20%. Okay. So 20% is 1/5. There are 5 colors. One divided by 5 is 20%. That's why he's looking at 20%. Write the appropriate hypothesis hypotheses to test Willie's claim. So your null hypothesis is always P equals. Okay. Uh, Mike, you said you and I have the same P hat? That's crazy. Uh, what are the chances? I know the chances. I know the. Uh, so Gabby, your P hat, P is a probability. All of these numbers that I was listing out here, P hat, P zero, P value, alpha, all of these are probabilities and they are between 0 and 1. So yeah, 0.146. That sounds better. There you
That was
go.
what I was trying to type.
Okay. All right, sounds good. Um, your null hypothesis is always P equals, so P equals 20%. For our alternative hypothesis, do we want to do greater than, less than, or not equal? Raya says not equal, except it looks like the emoji for the slanty face. Yeah, not equal, yeah. There's no not equal sign on the keyboard, right? So, uh, not equal to 20%. So he's not saying that it's more or less. He's just saying that it's different. Now, that is important, okay? Uh, whether you do a one-tail test, which would be more than or less than, or a two-tail test, which is not equal, that does change your result, okay? It changes your p-value, okay? It makes it harder to reject the null hypothesis. Um, so just be aware of that. And by the way, we mentioned earlier that you should be setting up your hypotheses before you do your sample, okay? So we shouldn't actually know whether we're looking at more than or less than. Because here I'm looking at it and it's less than. So why didn't I just say it's less than? Okay? Because if I didn't have a sample in place, then when he comes to me and says that the percent of purple is different from 20, he doesn't know whether it's more or less. Okay? He just knows that they're not doing the same amount of each color. That's the key. Okay? Anyway, now that I have this, we need to check our central limit theorem conditions are met. We need to check and make sure that it is a random sample, independent, and normal. Okay. For random, yes, because every Skittle had equal chance of being in my bag, right? Equal chance of being selected for the sample. Okay. I didn't just go pick out all the purples. Independent, I need 20n to be less than n. So my n was 238. 20 times 238 is 4760. Is that less than all Skittles? Heck yeah, it is, right? Definitely. For normal, I'm going to check NPQ, and I want to do P0, Q0, because when you're checking your central limit theorem conditions are met, you don't actually know P hat yet. You haven't done the sample yet. You don't know. You have to make sure that your sample size is big enough before you do the sample. So you have set your hypotheses, yes, and you can use that P0. You can't do P hat. Okay. Now with confidence intervals, we did N P hat Q hat, and that was because you don't have a P0. You don't have a number you're testing against. Okay. So when we were doing confidence intervals, yeah, you had to use what you had. Okay. So my N was 238. P0, everyone's P0 for this is 0.20, and that would mean my Q0 would be 80%. So 238 times 0.2 times 0.8 minus 38.08. Bigger than 10? Yes. Anybody get a no on this one? Gabby got 15. Yeah, that's still a yes. Yep, sounds good. Anybody get a no? How big of a sample size is needed for this one? 10 divided by 0.2 times 0.8. So if you had a sample size of 62, you got a no. If you had a 63 or higher, you got a yes. So did everybody get yes on this one? We had a couple of no's this morning. So okay. Sounds good. So even if you did get a no, that's totally fine. For question number 10, regardless of whether or not the conditions are met, test your hypotheses using your level of significance from number 2. So we said that we're going to use this alpha for Skittles. We use our first one for M&M. So I got 0.029 and 0.023, which are pretty close. They're not the same, but that's my new alpha. So step 1, I'm going to write out my hypotheses. Even though I did that already, I'm going to write them again. 20%. And my null hypothesis, and my alternative hypothesis, not equal to 20%. Step 2, my alpha was 0.023. Step 3, I'm going to write out formula for my z value, which is on page 262, p hat minus p0 over p0 q0 over n. Substitute in numbers. So my p hat was 0.176. P0 was 0.20. 0.20 times 0.80 over 238 was my n. So from here, I can either do Desmos and the normal calculator, or I can do what's on page 262 at the top, stat, proportion stats, one sample with summary. I'm going to do it that way this time. Stat, proportion stat. So I don't know my Z yet, but StatCrunch will give it to me. So stat, proportion stats, one sample with summary. I had 42 purples out of 238 Skittles. I'm comparing that to 0.20, and I'm doing not equal. Okay. I don't need the p-value plot. You can get it if you want. I'm gonna hit compute, and my z is negative 0.9075. Okay. There's my z value. Negative 1.3. Yeah, my z is tiny. Negative 0.9. That's very close to zero. There's no way I'm rejecting the null here today on this one. All right. If you got a large z like -2 or -3 or +2 or 3, then yeah, you're going to be rejecting for sure. Here's our normal curve. And my z value and my negative z value. Here's my z0 and z0. It's a two-tailed test, so I'm shading in both sides. When we were doing confidence intervals, we shaded in the middle section and left these sides blank, right? These are my alphas. Now I'm comparing my p-value to the alpha, right? So I'm shading in the tails now, okay? Because I want to compare this p-value to my alpha. So these two together add up to my p-value. And the p-value I got from StatCrunch is 0.3642. That is a massive p-value. Like I said, no way I'm rejecting this today. So p-value 3642. Compare that to my alpha, 0.023. Okay. My p-value is bigger, so I do not reject the null hypothesis. Did anybody get to reject the null hypothesis here on this one for Skittles? Oh, I wrote step 4. We already did step 4. That was step 4. This is step 5. Sorry about that. Did anybody reject the null? Show me how you get the p-value. Sure. Jalen rejected the null. Nice. So we do stat, proportion stats, one sample with summary. As at the top of page 262, stat, proportion stats, one sample with summary. I put in how many purples I had, how many Skittles I had, compare that to my p-value, which in this case is 0.2. Everybody's is 0.2. That's p0. Everyone should have the same p0. Not equal, and I hit compute, and that gives me my p-value right here. It also gives me my z-stat, okay? I mentioned don't check this button. If you do check that button, you're going to get two z values, and that's confusing. I get a z-stat and a critical z. Um, so which one do I write on the paper? Well, yeah, so don't check that button. Don't get this one because that's just going to confuse you, okay? Why that is why that happens is so in some other classes, you might not compare the p-value to the alpha. Every p-value, every probability has a corresponding z-value. And so what you could have done is you could have found the critical value for alpha, and that gives you a z. Um, so you didn't have to compare the p-value in the alpha. You could have compared the z null and the z value for alpha. That's just confusing. We're not going to do that. We are going to stick with comparing the probabilities. We're going to stick with comparing the p-value and the alpha. So, yeah, don't confuse yourself on that. Are z-stat and z-score different? No, they're not. They're both z values. So, yeah. So I'm going to get rid of this. Don't check this box when you're doing hypothesis testing. You should only have the one z value that you need to pay attention to. Yes, z-stat, and z-score are the same, Quinn. They are the same. Okay, so I missed my last step. Sorry about that. I got to write out my interpretation. There is not sufficient, and that's mine is not. Yours might not have the word not. You might say there is sufficient evidence. Sufficient evidence to support the claim. that the proportion of purple Skittles is not 20%. There is not sufficient evidence to support the claim that the proportion of purple Skittles is not 20%. Okay.
Hey Joe,
Mm-hmm.
um, I'm I'm having trouble. Is 0.1846 more than 0.071?
Hold on. Say those numbers again.
Zero
Zero
point
point.
one eight four six.
That's your p-value.
Yes,
And then alpha, what was that?
0.071.
1. So which of these is bigger? Um, so if it helps to think of these as percents, you can. You move the decimal twice. This is 18.46%.
Okay.
I move the decimal twice here. This is 7.1%. Which of those is bigger,
18.
right? Absolutely. So most people feel comfortable with percents. They don't feel comfortable with decimals all the time. So if that helps you, that's fine. I tend to do the switch in my own head. When I see 0.1846, I automatically think of that as 18%, but I'm used to doing that, because I've been dating this for, 15 years. So, uh, yeah, um, that's fine.
So I do
So
not
if
read.
this is the case, you do not, yep, do not reject. And there's not sufficient evidence. Yeah, so uh okay. Um Question 11. Which test had a higher chance of a type 1 error in the setup? So the probability of a type 1 error is your alpha. And I had an alpha of 0.29 or 2.9% for my M&Ms. And my probability of a type 1 error, my alpha for Skittles was 0.23 or 2.3%. So in my case, the M&M was slightly bigger. So we'll circle that one. Now, if your Skittle alpha was huge, you would circle the Skittle one, right? Whichever alpha was bigger. Okay. So alpha is the probability of a type 1 error. Question 12, which test had a higher chance of a type 1 error in the setup? That's exactly the same question as number 11. Yeah, that's a typo. It used to say type 2, and then I told her, hey, you need to change that, and she changed it to type 1, and now it's the same, so it's still not right. Uh, so the probability of a type 1 error is alpha. We've been talking about alpha this whole all day today. Okay. We're going to continue talking about alpha forever for the rest of the semester. The probability of a type 2 error is not alpha, it's beta. And we have not looked at beta. Beta is the power of your hypothesis test, and we are not going to calculate beta in this class. We might mention it, but we're not going to calculate it. Now, you would think, oh, well, if my alpha is bigger in this case, then my beta must be bigger in this case. And you'd be correct if the sample sizes were the same. Okay. If I have a small alpha, right? Because alpha is the probability of a type 1 error. I don't want to make errors. So I want my alpha to be very, very small. But if you make alpha small, then that makes your beta large. And the probability of a type 2 error is your beta. So you don't want that to happen necessarily either. So if you make your alpha large, then that makes your beta small. Okay. However, alpha is not the only thing that plays into the calculation for beta. The other thing that matters is the sample size. If you had the same number of M&Ms and Skittles, then I would agree with you and say, yep, if you circle this one, then circle the other one. Okay. I did not have the same number of M&Ms and Skittles. I had 140 M&Ms, but I had way more Skittles. I had 238 Skittles, almost 100 more. Okay. And if that happens, then it is possible that M&Ms had the higher chance of a type 1 error, and they also had a higher chance of a type 2 error. Okay. Like if I had 100 M&Ms, but I had a million Skittles, my Skittles results are going to be very accurate. And so my M&Ms are going to be a hot mess because I didn't have a very big sample size. Okay. So go ahead and answer number 12, however you want to answer number 12, because not only was it a typo, but even if it was typed out correctly, we still couldn't answer it. Um, so Isaiah's asking, what if you were off by 5? Then your sample sizes are very close, so close that I would say that they're practically the same. And in that case, you would say, okay, my M&Ms had a higher type 1 error, my Skittles had a higher type 2 error. Gabby had 105 M&Ms and 96 Skittles. That's a difference of 9. I would say that that's close enough to say, yeah, if you circle this one, then circle this one. Okay. But I'm not going to mark you off whatever you choose for number 12. Okay. I might show you the beta curve. Like I said, we're not going to calculate it or anything like that, but we might talk about it more. But for now, uh, that is it. Um, I did want to mention one thing about this right here. Um, so we did a two-tailed test, yes, and I got a massive p-value. If I had done a one-tailed test where I switched this to less than, I get the same z value, but I get a different p value. Okay. Why that matters is I said earlier, every z has a corresponding probability that goes with it, and every probability has a corresponding z value. So if I have the same z value, how did I get two different p values? And it's because when you do a one-tail test, this right here is 18%, okay? And I only have that. If I have two of those, then 18 plus 18 is 36%. So that's where this came from. Why that matters is because when you're comparing your p-value to your alpha, if you have a two-tailed test, your p-value is going to be twice as big as if you had a one-tailed test. Okay. So you do need to pay attention to that because it can change your result. Okay. Wouldn't change my result here because 18% is still way bigger than 2%. But if you have a two-tailed test, it's going to be harder to reject the null. Okay. The other reason why that's important to point out is we set up our hypotheses before doing the sample. At least that's the way you're supposed to. And after you set up your hypotheses, you can't go back later and say, oh, now that I see that my p hat is small, I'm going to change this from a not equal, I'm going to change it to a less than. Okay? Because then you're changing it from a two-tailed test to a one-tailed test, and you're not allowed to do that. When you're a researcher, you almost always want to reject the null. Okay. Researchers want to reject the null. They want to be able to say that their vaccine is effective. You want to be able to say that your car is safer than other cars. You want to be able to say that your commercial is going to be more effective than your new commercials more effective than your old commercial. Okay. So if it's equal, if your new commercial and your old commercial are equal in, effectiveness, then you're not increasing your sales. And that sucks, right? Researchers want to reject the null, but just because you want to doesn't mean you can change your results, change your test from a two-tailed test to a one-tailed test just so that you get better results. Okay. So be aware of that. So that's all I had. Let's call it a night. If you have questions, stick around. I did record the entire session, and we'll do more hypothesis testing on Thursday. Let me know what you want to do about April 16th in that poll, whether you want to meet in the morning and watch the Zoom in the evening, or if you want to just push everything a day later. So talk to you guys later this week.